When human drivers face heavy rain on a dark highway, our vision fails. We slow down and squint, but autonomous vehicles are designed to rely on sensors meant to see through the storm. That assumption is flawed. Radar pierces through rain and fog, but it breaks down when trying to process complex, metallic environments like modern highways. The problem lies in ghost objects. Radio waves bounce chaotically off large metal surfaces, like semi-trucks or guardrails, creating false positives. These ghosts mask the weak signal of a pedestrian, effectively hiding them from the vehicle's computer. This sensor confusion leads to phantom braking or worse, missed targets. Currently, radar is too unreliable to serve as a standalone safety foundation for driverless cars. This instability stems from the sparse aperture deficit. In a busy scene, physical scattering centers far outnumber the car's antennas. This creates a massive data bottleneck, causing traditional radar setups to miss actual targets almost 60% of the time. For years, the industry tried to fix this with software, using black box neural networks to aggressively filter out the noise. That filtering was dangerous. The AI often could not distinguish between a radar ghost and a weak true target, meaning the system frequently deleted real humans along with the noise. LiDAR was often proposed as the alternative, but it remains expensive and fragile. More importantly, LiDAR fails in the exact same heavy weather conditions where radar is most needed. The industry hit a mathematical ceiling. Billions in software development could not recover physical information fundamentally missing from the sensor data. Finding a way forward required looking at a completely different field, high-precision medical imaging. Dr. Behrooz Rizvani and his team at Automatic weren't trying to build a better car sensor. They were analyzing the basic mathematics of how signals are processed. They realized the radar sparse aperture crisis was mathematically identical to an existing problem in medicine, reconstructing high-resolution images of human tissue from sparse MRI data. Medical researchers use a framework called the atomic norm to pull anatomical detail out of chaotic, sparse data points. By applying this medical algorithm to automotive radio waves, researchers discovered a way to resolve radar data with clarity that was once considered impossible. Instead of filtering data away, this architecture works backward. It mathematically decomposes chaotic signals into discrete physical sources. The AI then performs multi-hypothesis testing, generating potential realities for every radar return and checking them against the strict laws of wave physics. If a signal represents a physical impossibility, the reasoning engine instantly rejects it as a ghost. Only physically verified objects remain. This isolates weak signals even in high dynamic range scenes. A pedestrian standing next to a massive reflective truck is clearly identified rather than drowned out. This physics-constrained reasoning removes the sensory errors that hindered early autonomous vehicle development. Because the software cleans the signal at the waveform level, vehicles can achieve high precision with significantly fewer antennas and hardware components. This shift is forcing industry giants to recalibrate their sensor stacks, which have long been burdened by expensive, protruding LiDAR hardware. Manufacturers are moving towards fusion strategies, where radar is stable enough to act as the foundational safety layer in all weather conditions. The implications are massive, arriving just as the global automotive sensor market is projected to reach over $14 billion by the end of the decade. Closing this perception gap changes the unit economics of self-driving technology, turning expensive prototype fleets into a viable option for mass market integration. We are seeing the early stages of this shift today. Autonomous 18-wheelers are beginning to utilize this technology to safely run 24/7 logistics routes down dedicated highway corridors. The ultimate goal is a drastic reduction in the thousands of fatal crashes caused annually by human error and sensory blindness. Safe, reliable autonomy finally became possible because of the same mathematics used to look inside the human body. Subscribe to the channel for more breakdowns of the scientific breakthroughs reshaping our future.